Hello, and welcome back to the third video in our series on the Frene-Serie transformations and plotting a helix with its special pipe outline. So just a quick recap from my previous video. I finished recording everything, went to go grab my back cam, because I have my frontward-facing me cam, my front cam, and we also have to have a back cam. Runtime just disconnected and reconnected, unfortunately. But I went to grab my phone to get the footage from behind, and my phone was powered off, which was strange because it was recording when I started. And then I realized that my phone had died. It had run out of power mid-recording, and because they don't record in NKV, because it's an Apple phone, that video footage is entirely lost. So I still have the video of me doing the coding and the video of me talking to you while I'm doing the coding, but unfortunately there's no back cam. So I apologize for that. So that really put me in a not a happy place. I was very, very upset with that because that tape was wonderful. But we keep on trucking. So we're going to keep going with this. We're going to work on our next part, which is going to be actually using the tangent and normal unit vectors we just found in our previous video, and using them to finally finish the third unit vector of our new mobile framework for building things. Because again, we're building a framework of units, or not units, a framework of axes which moves along with our curve. So by calculating these axes every single time our curve moves, we can pretty accurately, and by pretty accurately I mean completely accurately, build things off of that location that is moving. So we have a moving framework. So it's a lot easier to do in Python than it is to do drawing, because my hand-eye coordination is bad. So let's just get right into it. So what we're going to do now is we're going to define a new function. And this function is going to take in some specific time along our curve and some specific angle along our curve. And the reason we're not setting it up to do arrays is because we're going to do matrix multiplication. And so doing that would require like 3-dimensional and 4-dimensional arrays, which as a new array programmer I'm not quite used to yet. So we're gonna do for loops when we actually implement it for our final actual graphing, where we have to get all of those sets of points. So for now we're just gonna stick with some pretty simple stuff. So what we're trying to do is we're trying to plot all of the points. I mean, at this point we're just getting one set of points. But eventually when we put it in the for loops, we're going to give it a time, which we're going to give it a range of times, and we're going to give it a range of angles. But for the implementation, the way we'll be thinking about it right now is we're going to give you a time, and we're going to imagine a set of angles, but just one specific angle. And at that time, with that starting location, we're going to have to figure out where we are in the XYZ plane. Then we're going to have to figure out where, relative to the point we're looking at in that XYZ plane, our offset would be in the XYZ plane from that. But then we have to take that offset, which would be sine and cosine, bring it into the n and b coordinate system we're about to create, adjust it there, and use that adjustment factor to make sure those adjustments are being exhibited in the XY plane, the real XY plane that we're actually looking at correctly. Probably super muddly to explain out loud. Best example I can think of off the top of my head would be satellites, where we launch them obviously off of Earth. So when we're saying they're moving at 300 miles an hour, it's 300 miles an hour plus however fast the Earth is moving when they were launched. But once they're in space and they're dealing with other orbital bodies, suddenly the Earth is no longer a good reference position. So if we want to move it another 100 miles above the Earth, but we're now using the Sun as a reference position, we have to make sure that we translate moving a certain direction away from the Sun 100 miles is actually moving the direction we want away from Earth 100 miles. So this coordinate system we just worked on is essentially that translation factor between the Sun coordinate system and the Earth coordinate system. It's just that the Sun coordinate system is the NB coordinate system that we just developed that moves along with the Earth. Or I guess it'd be backwards, that the Sun would now become our new reference X and Y, our absolute center, and the Earth would be our new NB coordinate system. But again, I digress. That's just a bad example that I came up with off the top of my head. So let's just get right into coding. So the first thing we're going to need is we're going to know the radius. How far away from the center curve are we trying to put our spokes? So I'm going to just call that R inner, Rinner, and I'm going to set that equal to 0.5 because that's just the value we've been given to work with. So the next thing we're going to do is we're going to just define our function. So we want to define a new function, and I'm going to call this pipeline, because I can, pipeline. because this is going to be the outline of the pipe. This is going to tell us every single point. Again, once we feed it in a vector of times, and then for each vector of time, for each element in a vector of time, not a vector of time, why do I keep saying vector of time? For each element in a set of times, an array of times, we're going to go through and have an array of thetas, and we're going to go through each of those thetas to figure out every single point along the circumference that will be associated with that point. And then once we do that for every single time, we'll have a set of rings going around it, and then from there we'll connect it. That's all the fourth video. But anyways, that's why I'm calling it pipeline. So our pipeline is going to take in some time and some angle theta. And what we want it to return is the coordinate, like an array of coordinates that represent this. So obviously what we're calculating here is the offset. And we're going to be adding that to the original. So since I want the actual I want to just be able to plot whatever this thing spits out and have it work, we're going to take whatever our curve value is at time t, right? So again, if we're thinking of our curve at, like, say, time 0, so we know it's on the floor, so it's at 0 on the z coordinate and 0 on the y, and it's at 0.3 on the x. So we want to take that and we want to add to that set the offset we've calculated as a result of using our new thing. So I'm just going to call that, not offset, I'm going to call this circumference vec. Because it's a vector, right? It's going to tell us, this is going to be telling us our offset in x, y, and z coordinates thanks to the n and b translation we did. So how do we do this? Well, the first thing we're going to have to do is define, like the whole reason is to figure out what the normal is, what the tangent is, what the normal is, and then the cross product between those two to give us our third coordinate system. And the reason we need that is because we want our circle to be not at all related to the tangent. So if you were like driving your car, right, you'd want it to be going around the body of the car by the doors, and you wouldn't want anything obstructing your view. That kind of thing, like a ring around it. So the center of the circle is going to be on the tangent line, and the circumference is going to be completely surrounding it, like radially symmetrical is probably the right word to describe that. So what we're going to have to do is we're going to have to figure out what that vertical axis is, because again, if we're considering the point on our curve to be our new origin of this new n and b coordinate system, we're going to take those coordinates and then translate them into our old coordinate system that we've been using through this n and b coordinator. But we're going to need to know what b is because we want the vertical axis. We need x, which in this case is going to be our normal, and then y, because our tangent is the one that's kind of our perspective, our POV. So I'm going to just make capital T is our tangent, and that's just going to be, well, the function we just made called curve tan at time t. Next thing we're going to need, I don't know why I hit enter, I could just go down. Next thing we're going to need is our normal unit vector, which is just going to be curve normal, again at time t, because we're going to be iterating through this pipeline function. So maybe instead of a pipeline, because we're not actually spitting out this function is specifically putting out a single point. So maybe we'll call this pipe point instead of pipeline, but that's fine. So curve normal, and then what we need now is our b, our cross product vector. But that's really easy. It's just JNP dot cross, and then we're going to just list the two things we want to cross. So t and n. Those are the two things we're taking a cross product of. So now we have our three axes. T is like the equivalent of, I guess it would be the x. I'm just going to go with x because it's facing, this is the perspective. It's right here. So it's facing into us. And then this one are kind of horizontally one, because again, I'm using your perspective of the camera right now. This is going to be our kind of y coordinate, sort of. So this is our n. And then b is up here. So again, when we're starting at the angle 0, it's going to be 1, 0. I should probably do this in a way that's more easy to see. Right? It's going to be nothing vertical, only horizontal. And then as it switches like that, as we go around the circle. So anyway, we have our three things set up. So we're going to not really use t any farther now that we've gotten our n. So what do we want to do? Well, what we want to do is we want to take each point based off the angle and figure out what it is relative to the point that we're considered, like the old. I'm not going to trip over my words here. We're setting our current origin to be the point on our curve that we've just calculated. So, relative to that, how far is our offset. So we know our radius from that point is 0.5, and we know that what the x and y component of that origin will be is just going to be sine and cosine times the angle from that point multiplied by the radius of that point. So I'm just going to call this I'm just going to draw the array first. So it's going to be jnp dot array parentheses brackets space, and it's going to be, we're going to do our x1 first. That's just going to be rinner times jnp dot cosine of theta followed by rinner times jnp dot sine of theta. And yes, technically, since this is a vector, I could theoretically, I spelled rinner wrong. It's fine. Since theoretically this is an array, I could put this outside of multiplying by the array, but I just don't want to do that because it keeps it straighter in my head, because I know I'm multiplying by the radius times the x coordinate and the y coordinate. But again, these aren't actually the xy coordinates. These are according to our center being on the curve. So this is really in n and b space, because what we've calculated up here with our unit vectors is letting us convert between nb space and xy space, or I guess it'd be yz space, because that's the plane in which we're doing it in the example I've been giving. But again, it doesn't matter because n and b are constantly shifting, so it's not like there's two letters, except I guess z is always up still. But that's all a digression. So we have this. This is going to tell us, where around a certain point on our actual curve we're looking at for the pipe point. So I don't know what to call this. We can just leave it. We don't have to necessarily do anything. So now what we want to do is we want to transform this from the x and y coordinate that's based on the curve point to the absolute, global coordinate system. So we're going to do that by doing a matrix multiplication with our n and b vectors. So how do we do that? Well, if we recall, what comes out of n is a vector with three components. It's a one-dimensional vector. It's almost like a list where it has the x coordinate, the y coordinate, and I gotta make sure x, y, and z. And b is the same thing, because it's a cross product between these two vectors of size 3. It will also have three vectors, the x, y, and z coordinate. So what we want to do now is do matrix multiplication. We're going to take each value of, each conversion factor between n and x, let's say, and we're going to multiply that by the x coordinate of this and the y coordinate of this. And we're going to do the same thing with b, because they each have their own conversion factors. So how do we do that? Well, matrix multiplication multiplies a row with a column. So that's what we need to do. So we need to make sure that the three n's are vertically stacked, because we only want this right here, the x coordinate, to match with the n coordinate, and then we want the y coordinate to match with the b coordinate. So to do that, we're going to stack n vertically and b vertically, like two towers, and squish them next to each other. So how do we do that? How do we make that the shape? Because if we were to just combine them, they would either combine in a line like n1 xyz and then b xyz, or they'd stack vertically where it'd be n xyz, and then below that would be b1 xyz, and we don't want that either. We want them to be stacked vertically. And the way we can do that is actually using a function called jnp.stack. What this will do is, I'm going to just put the matrix multiplication sign in there, so we'll get out of the way. np stack, if it will tell me what it does. There we go. So we give it a set of arrays, I think separated by commas, and we tell it which axis we want it to stack them on. So since these are both one-dimensional arrays, we want them to be stacked along the second axis. Because again, if our n is like this, and our b is like this, we want to make sure that the n goes this way and the b goes this way so that they can be standing next to each other, and we only get one of each at a time, one finger segment of each at a time being cross-multiplied with this horizontal array. So we're going to want our axis to be 1, and we're just going to list our arrays. So it's going to be, let me make sure that I'm just going to put arrays and figure out what that. Arrays is a sequence of array likes. Okay, a sequence. So is that a? I think that's an array of arrays. So I'm going to try with a list it might have to be a specifically array of arrays, but I think we're going to try this for now. So we want N, we want B, and what do we want them to do? We want them to be stacked vertically, so along the second axis. So axis is equal to 0, because axis is equal to 1, because we're kind of rotating them 90 degrees when we stack them, if you think about it like that. So they're laying flat, we stand them up onto their first axis, and then combine them together. So now that's it's a 3 by 2 matrix instead of a 1 by 3 matrix. This is circumvec. This is the vector we've been looking for, because this has our xy coordinate of some point along that circumferential circle that that's following the actual curve. It's been translated into the global positioning system that we've been using up to this point through this JNP stack matrix multiplication conversion factor, essentially. And then we're just adding that onto the location of that the point on the curve we were focusing on, which again is in our global positioning system. So if this works, it says it worked. So, for example, if I were to run pipe point at t is equal to 0, so 0 point, not no point, 0 point, and I were to run it at JNP angle of just at 0, an angle of 0. That will just work. Here we go. So we've got a location of 2.5, 0, and 0. So what does that mean? Well, if we go back up here to our graph, and our graph has these points on it, and I don't like that, so I'm just going to quickly make it in line mode. So mode is equal to lines. Oh, I forgot to put my little... Rerun that curve. There we go. And it's also kind of choppy, so I want more points. I want it to be very... Actually... No, it's fine choppy, because it lets me see. So this is our first point right here. Navigate around a little bit. Right here, we're at point 300 in the global XYZ plane. And you remember it said 2.500. So if we look, 2.5 is right here. That's half 0.5, a unit, 0.5 units inwards. So if we think about it, this is angle 0. And that makes sense, because our theta angle, our x coordinate, what we're basing it off of, is that n vector. And remember that the n vector, the normal vector to our curve, represents its acceleration. If we were to use tangent, if we were to conflate tangent with velocity, it would be our acceleration. Since whenever you're doing circular motion, you're being accelerated inwards towards the center of that circle, it makes sense that if our unit vector is pointing this direction, it's saying this is positive. So that difference we got of 0.5 is magnituded inward. So when that's subtracted, or I guess it would be negative, because if we remember before, the unit vector was negative from the previous thing. So the unit vector this direction is considered negative. So when you're adding in a negative 0.5, it decreases it to 2.5. But the other two were still 0, because at this angle, we're not looking vertically. But if we were to change this to, this is the angle, is the second one, we were to change it to JNP dot pi divided by 2, now our x-axis is at 3, which makes sense, because now we're pointing straight up into our b direction. So our x is still at 0.3 at this point, so it should be sitting directly above the curve. But we notice that it's got 2 points here. It's got a very small y and almost 0.5 z. So it's almost straight up, but it's leaning negative in the y direction. But let's take a look at why that is, just to prove that this is working. So I'm going to switch away from the x perspective, because we're not changing an x, so we can get rid of that. So if we look right here, you'll recall that, again, this is a kind of a slinky that's trending upwards over time. So if I could get my z-axis actually in here without my x, would be great. There we go. So you'll notice that because we're going upwards, we're constantly at an upward slope, which means that our b vector, our unit vector, our cross product that we just calculated, isn't pointing straight up. It's pointing straight up relative to the slope of our curve, relative to that original vector. Remember, it's a cross product of the acceleration and the velocity, so to speak. So it should be perpendicular to where it's going and how it's being accelerated. So considering it's moving upwards, it can't be straight up because there's a component of our movement that is also upwards. So we actually have a slight backwards slant kind of towards this point right here, where it's both going mostly upwards, but also a little bit to the left of that from the perspective we're looking at now, because it's slanting away from the uphill climb of our curve. That's working as intended. So, just to prove that, because what we're going to do next, as I said before, run it through an array. So I'm not 100% sure if right now it will just work if I just throw an array in, so I'm going to try. So I remember I defined a t already from 0 to 5 fours. So I'm just going to copy that and put it down here just so I can see it again by me. And I'm also going to make a theta, which is equal to the exact same thing, but obviously it's not going to be to 4 pi, it's going to be to 2 pi. And we're going to have, again, 50 more points. So now if I do it if I just plug in t and theta, this may work. If it doesn't, that's all right, because we can just do a for loop when we implement it in our 4th video. No, theta is going to be, that's the name of it. Will you run? Oh, it's cranking. Mentions with being either 2 or 3 for cross product. Yeah, it figures, because this is meant to return, this is all meant to return something at an individual point. I was pretty sure it wouldn't work, but yeah, because this is only meant to return, you're meant to return for a single t. But if I were to, for example, do A, comma B, and then just, you might like this. And I said, for A in T, for B, actually I should probably do for B in theta, for A in T. This is a list comprehension. This is basically doing a double for loop. So for every B in theta, I think in that order. I'm not totally sure which way it reads double for loop if list comprehension. But the fact that it's chugging and it hasn't crashed yet means that it's probably actually working. It's just probably not very happy about doing that 51 times 51 times. Because for every single t, there are 51 thetas. So we're going to actually cut that right now, and we're going to drop this down. I'm just going to call this t circ just to make it smaller. And we're going to cut this down to 21, maybe. That's still a lot. Maybe we'll do 11 circles, and for what we'll do, I'll just cut it down to 11. T circ. Now go. This should go a lot faster, hopefully. Because again, remember, it has to calculate the. It's individually right now calculating the b's at every single one of those points. Oh, and here we go. So we start off with 2.5. And then we end up with positive 2.5 again. So let's see. I'm not entirely sure which one it did first. That's some list comprehension stuff I should probably know. But we can always just swap these around and see if this looks any better. Might take a second again, but I do want to know this because I'm curious. But either way, we proved that it works. This one looks a lot more organized, I think. Yeah, here it is. Okay, so this is what we wanted. So this is going at a certain, this picks a t, some a in t, and it goes through and it cycles around. So we're at 2.5 in the x, cycling around all the way back to 2.5. Then the next point from 0.7 all the way around to positive 1, back down to 0.7. This one's from negative 2 all the way to, well, there's a bunch of 2 negative 2's in a row, but I'm guessing they're similar. But anyway, so this works. So if we were to plug in a series of individual points into this, we could get specifically what the offset is from the curve. And then by just adding that to the curve, we it just tells us the point in the global positioning system we were using previously, where it is. So I think this is definitely a success. We're getting all the device arrays we could ever want or hope for. Because next what we're going to do is we're going to basically make it do this, but way faster by actually turning our function into a vector. So keep the eye out for that. That's all for this video, though. Thank you for tuning in. I really appreciate you watching. So thank you, and have a good evening.